Oh, hey guys, we're on 1-8. This is kind of where we start in on scientific notation. This is using powers of 10 to estimate quantities. All right. So on this one, we have these two guys, Keegan and Jeff. They did some research and found that they're approximately, I don't even know. Let's see. Million, billion, trillion, quadrillion. Man, I got to look that up. So 7, let's look it up right now, right? After quadrillion. Trillion. No, million, trillion, million, billion, trillion, quadrillion, quintillion, sextillion. Golly. Okay. All right. So, got it. So let's see. That's millions, billions, trillion, quadrillion, quintillion. So 7 quintillion, 492 quadrillion grains of sand on Earth. Jeff says this is about 7 times 10 to the 15th grains of sand. Kevin says it is 7 times 10 to the 18th grains of sand. How might Jeff have determined this estimate? How might Keegan have determined his estimate? Well, I like just counting out how many spaces there are, right? Let's count out how many zeros we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, there are 15 zeros right here. That makes sense. But there are actually 18 spaces. Like if you count that's 15 right there, 16, 17, 18 right there. So for Jeff, I'd say he counted zeros. So he counted how many zeros there are. And then for Keegan, he basically counted up to the 7, right? He counted up to the largest digit, basically, right? Right, so they're kind of 18 spaces, right? Okay, so if that's 15, then 16, 17, 18 right there, right? So then you would put a decimal point right there. Okay, so that's kind of the idea right there. Whose estimate, Jeff's or Keegan's, is more logical? Well, I already know the answer. It is Keegan, because you actually count right up. You basically move your decimal, right? So if you have it here, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's how you end up doing this, right? Whose estimate, Jeff's or Keegan's, is more logical? Well, I'd say Keegan's is more logical because he was using he used all of the digits basically instead of just the zeros. Yeah. Use all of the digits instead of just the zeros. Yeah. So yeah. Oops, because he used all the digits instead of zeros. That's kind of blue, make sure. So I'm going to hope that I have blue here. Yeah. Okay. Yeah. So light travels 299,792,458 meters per second. Sound travels at 332 meters per second. Use the power of 10 to compare the speed of light to the speed of sound. Actually, hold on, I gotta pause this for 1 sec, guys. All right, we're back here. Oh, sorry about that, guys. Just had some reason. So the idea here is you take kind of each number here, and we're going to compare how big they are. We're going to use powers of 10 or exponents to do this. Okay. So you round it to the biggest place value, right? So this 299,000 basically just rounds up to 300 million. Okay. So for the speed of light versus the speed of sound. Okay. So we've got 300 million right here. Okay. And then for the other one, we're going to round it down a little bit to go to 300. Okay. So that's the kind of the idea. It just makes it easier to compare these things. Okay. And so then use the power of 10 to compare the speed of light to the speed of sound. So you, let's see if I can write this in green. Round to the nearest place value. Round to the largest place value. Sorry. Round to largest place value. Okay, you count your zeros. So that's kind of step one. Step two is count your zeros. Okay, so let's see, in this one we have 1, 2, 3, 4, 5, 6, 7, 8 of them. So since we have 8 of them, we can actually just pull this and just be like 3, and then we multiply it by 10 to the 8th, because 10 to the 8th gives us all those zeros right there, and then we just plop that 3 on the end of it. Okay, so it's basically like moving it over, right? Moving the decimal piece, right? So 1, 2, 3, 4, 5, 6, 7, 8. So that's the idea. Now we count 2 zeros right here. So 1, 2. So this becomes, so this has 8, and then this has 2. And so this becomes 3 times 10 squared. Okay, so round to the largest place value, count zeros, and then you want to put it in scientific notation, right? And we're going to talk a lot more about scientific notation over the last couple of days. So I just kind of want to introduce that vocabulary to you, right? So 3 times 10 to the 8th represents that 300 million, and that 3 times 10 squared represents that 300. So you can see that there's a difference of 6 exponents, right? 6 factors basically of magnitude. So that's much, much faster. Speed of light is much, much faster. Country has a population of, it's like 1 billion. And then country B has 1,238,000, and then 1,106. So what you can do with this, rather than counting the zeros or rounding, you can actually kind of just count the spaces, right? So we want to kind of put our decimal point right there. So we just count how many we got. 1, 2, 3, 4, 5, 6, 7, 8, 9. So then we'll say 1.2 times 10 to the 9th, right? And it's the same number of spaces we're moving. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is 1.1 times 10 to the 9th. Right? So you can round it if you want to, make it a little bit easier, or you can put 1, maybe even 2 decimals. Like we could say 1.23 or 1.24. This would be 1.11, maybe if you rounded that. But I typically think scientific notation just goes to 1 decimal, maybe 2. Okay, now you can do the same thing rather than using very, very large quantities. You can do the same technique to estimate very, very small quantities. So Matthias is a lady who measured the average thickness of human hair, which is this right here. Okay, and then a sheet of paper is about 0.0013 meters thick. Right? How do the two thicknesses compare? And so you kind of do that same thing, right? We're going to, but instead of like moving your decimal to the left, right, we're going to move our decimal to the right. So if we have the paper here, actually we'll do the hair here on this left side. No. We'll do the hair over here because the picture of the hair is right there. And then paper is right here. Okay. So we have 0.0013 for the paper. 1, 2, 3. Right? And for the hair, it's 0.1, 2, 3, 4, 6, 3. Okay. So the idea here is let's do just a little bit of rounding. So let's kind of just, this would round down to 1. So let's see, 0.001, and this will round down to basically 0.0002, right? Because that 1, 7, right? And so then we move our decimal over how many times, right? 1, 2, 3. Yep. And since we're moving to the right, basically it becomes 1 times 10 to the negative third, since we're moving to the right. And we've seen negative exponents before, so it shouldn't be like a shock to you guys. And then for this one, 1, 2, 3, 4. So we moved it over by 4, so it's 2 times 10 to the negative fourth. If you're moving your decimal to the right, you have a negative exponent. If you're moving your decimal to the left, you have a positive exponent, okay? That's kind of the idea right here. So how did the two thicknesses compare? Well, your hair is definitely less thick than the sheet of paper. It's much, much thinner. than the sheet of paper. Yeah. Find how many times as much. How does the gross the GDP of Canada compared to that of the United States? That's basically how much production each company has. Okay. So we do that same thing, right? We'll do Canada here, Canada versus the USA. I'll give myself a little more room, right? So round to the near largest place value. So we'll say we'll do 1.8 for this, okay? And we'll do 1.7 for the USA. So 1.8. I don't really want to write this out, so I'm just going to count it. So let's see, for Canada, we move over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so that's 1.8 times 10 to the 15th. And then, do we want to do twos on here? Yeah, let's do twos. Let's actually round it up to 2 because we want to do 2 times 10 to the 15th. That's what the book is telling us, okay? So yeah, round it up kind of to that nearest, the largest place value, right? So this way we can compare the same base, right? And so for this one, we'll do 2. But instead of 15, we've got 3, 6, 9, 12, 15, 16. So it's 2 times 10 to the 16th, right? And so if we compare these, we have Canada, there's an A in there, just so you know. We have this 2 times 10 to the 15th for Canada. That is less than USA's 2 times 10 to the 16th, right? So yeah, just make sure you're kind of rounding to that nearest, because that way you can compare it a lot easier with these 2's right here. Rather than like 1.7 and 1.8. So that way you get the same base. It is much easier to talk about. So yeah, this is it right here. When you move to the left, you have a positive exponent. You just kind of count the zeros. And when you move to the right, you have a negative exponent. Just count the number of zeros to determine the exponent you put on the 10. When would you use powers of 10 to estimate a quantity? So many examples, right? In chemistry, when you're like trying to figure out how many, like if you're an environmental engineer, right? And you are trying to figure out if a company polluted the water, you need to figure out how much whatever chemical is in there versus the water, right? And it's typically going to be very, very small particles. So you're going to use like those negative exponents here to represent those very small quantities. In space travel, right? You have very, very large distances. So this is when you use, light years and things like that, which, from galaxy to galaxy, you have huge distances. So that's when you're going to use those powers of 10. Yeah, guys, that's about it right there. And fold it in half, hamburger style, el estilo de hamburguesa, just like so, right there. And then we're going to put this on page 15 using powers of 10. To estimate quantities, like so. Glue that in here. And then we'll do the table of contents. Like so. So page 15, 1-8, using powers of 10 for quantities. Let's just say that so we can fit it in there. Okay. There you go, guys.